Hi, I'm Mike Sayers from Mechanical Simulation. This video will go over the coordinate system used in the vehicle models in CarSim and TruckSim. If you are new to the software, it might help you learn about some of the output variables that describe the vehicle location and orientation in the simulation. The coordinate system is also essential for locating suspensions and other parts of the vehicle. For example, in this simulation at the racetrack, we have arrow vectors showing 5 different coordinate systems, one for each tire and the blue one for the vehicle Sprung Mass. Now, a Cartesian coordinate system has 2 parts. It has a set of axes that are perpendicular to each other and a point of origin. In this video here, we see that there is a red set of axes and a blue set of axes. The red set of axes are for a global coordinate system. Right here where they come out, this is the origin of the global coordinate system. In our models, we also have GPS, which is using angles of latitude and longitude. So the convention we have is that the x-axis is pointing due east, the y-axis is pointing due north, and the z-axis goes up opposite the direction of gravity. The axes in the vehicle follow the vehicle as it moves around. We use yaw, pitch, and roll. As we go through a little demonstration here, we see that the vehicle is yawing. The blue z-axis stays parallel to the red z-axis of the global coordinate system. And over on the right side, we have the yaw, pitch, and roll with numbers showing their values here, so we can see that we're taking the yaw and moving it up to 40 degrees. Now we'll go around here. The x and y axes are still parallel to the ground, but they're pointing in different directions than they were before. They're differing by the yaw angle. Next we'll pitch it. And when we do this, the y-axis of the vehicle stays fixed, but the x and z axes rotate in the pitch angle. Next, as you might expect, is roll. In this case, the x-axis stays fixed, but the y and z rotate around it. When we take a sequence of consecutive rotations like this, each angle is called an Euler angle. There are a lot of ways to do it. The one is standard in vehicle dynamics is to go yaw, pitch, and roll. Pitch is the smallest angle, which means it doesn't distort the roll as much. Notice in the plot up here that we have vehicle roll and Euler roll. Euler roll is what we just saw about the x-axis of the vehicle. The non-Euler roll is the angle you would get between the y-axis and the ground, and they're not the same. The angle to the ground is a little bit less. Let's look at where the vehicle coordinate system is set up. It's on the Sprung Mass screen, and the axes that we saw, the blue ones, the x, y, and z, are fixed in the Sprung Mass rigid body in the vehicle model. As shown before, the z-axis goes up, the x-axis goes forward. Where is the origin? Well, the model doesn't really care. It's what you use to provide a reference for all the points that you put in here. All the heights that you give are relative to wherever the x-axis is. You just have to be consistent. The same thing with the lengths. You have to be consistent with where the origin is longitudinally. Now here is the vehicle that we just looked at, the Sprung Mass, in a quick start guide scenario. The red axes over here are the origin and axes for the global coordinate system. We're going due east, looking west at the vehicle. You see that the y-axis and x-axes are hidden a little bit. They're underground. When we look at the plot over here, we see that the initial pitch is not 0, but it's got a slightly positive value, so that the car is leaning forward just a little bit. And as we saw from the side view, the origin of the vehicle, of the Sprung Mass coordinate system, is near the front by the center of the front wheels. Back on the Sprung Mass screen, the coordinates here apply when the vehicle is at 0 pitch and 0 roll. Notice that we have the heights of the wheel centers in that condition. 340 are the heights above this arbitrary reference for the front wheels, and 325 for the rear wheels. That's saying that when the pitch is 0, we expect the wheel center to be this far above the x-axis. If we change these, I mean, this has a huge influence. This pretty much defines what the nominal pitch angle is. Say I change these to 100. Now notice that that is the distance from the wheel to this line. That means I've lowered the wheels down relative to the sprung mass. Now I'm not going to push the ground down. The ground is fixed. So if I'm pushing the wheels down, the only way I can do that if I've got the same size tires is to lift the sprung mass up. And indeed, that's what happens. When we look at this, we see that the whole blue axis system is tilted forward. When we look at the plot over here, we see that the pitch is now almost 4 degrees going forward, because we said that these rear wheels are only 100 millimeters above the blue line here. The front ones are still 340 millimeters above it in the nominal configuration. Now the assumption is that these wheel center heights apply when the vehicle has its nominal load condition and the suspensions are deflected as needed to support that load. It's not directly taking the size of the tires into account, but the assumption is that you're going to have tires that are sort of typical in size. Our intent, though, is that you should be able to use the same sprung mass data set with lots of different loading conditions and even swapping out wheels. You've now seen how you define the coordinate systems that in turn define pitch and roll in car sim and truck sim models. Thank you for watching.